This conference will now be recorded.
Very good evening, students. Today we are starting a new chapter, alternating current. So, alternating current, in short, it is written as AC. So, alternating current. In short, it is written as AC or small in lowercase. Okay, so AC. And direct current. We'll see the definitions of direct current as well as alternating current. So, direct current is abbreviated as DC, okay, or small DC like this, okay. So alternating current and direct current. But when we say AC voltage, AC voltage or AC EMF, actually that doesn't mean that AC current voltage. It means alternating voltage. Okay, it means alternating voltage. Alternating voltage. All right. And DC voltage means direct voltage. That is all right. So DC voltage means direct voltage. Okay, so before we go into the subjects to be covered today's class, I would like to ask you one thing. So, why do you need alternating current? Okay, okay, let me just tell you before I ask the question that in our household applications, various appliances like heater, bulb, fan, etc., and many other instruments, electrical equipments are run by AC all around us. Okay. Obviously, there are instruments which are run by direct current, but in modern age, almost all electrical appliances are run by alternating current. So, why do we need alternating current when we had direct current? Obviously, there should be some reason for that. So there are two reasons actually why we use AC over DC. So there are two reasons. One is that AC can be AC can be AC can be transmitted excuse me. Okay, so AC can be transmitted safely and in and without much or uh, okay, without much loss, okay, loss of power. Even though, okay, I'll tell you what is done in case of transmission. See, long wave transmission, when we do, see, we are using power, electrical power, but that power, electrical power, is generated somewhere in Kalpakkam or uh, many other places are there. There are like power plants there. Okay, there are power plants, thermal power plants or hydro power plants. So there the power is, electrical power is generated, and that power is actually transmitted to long thousands of kilometers, okay, to distribute this electrical power, okay, and that is transmitted in terms of AC. Why? See, low voltage and high current is easy for, like, that is safe to use, okay. Low voltage and high current is easy to use or easy to consume for the consumers. Not easy, I should say safe to use, okay, for the consumer, but it is not safe or not cost effective for the transmission. So this is actually done in DC. In DC, the voltage is low but current can be high. So this is DC, but transmission is actually cost effective because loss will be very high. If we see, if we have I square R, that is the power, right? This is power. So this is the power loss, or loss, I should say, heat generated, or loss of power. Loss of power, I square R. If I make the current high, then loss will be more, and this is the case in case of DC, okay, where the voltage is low, current is high. But in case of AC, it is easily transmitted or safely transmitted when we make. See, in case of AC, what it is done, high voltage, high voltage and low current. So the transmission becomes, so this C I square R, this actually become less, okay. So the loss will be less. In another way, see, in case of DC, we cannot change the voltage or current, okay. Once, see, current and voltage cannot be changed. The magnitude of the current and voltage cannot be changed. The second point is that using transformer transformer we can increase or decrease the, or alter the, decrease the magnitude of the AC voltage or current whenever required, or current. But this is not done, or this cannot be done in case of DC. So there are two things here. So one is the loss, another one is that transformation, okay, using transformer, we cannot change the magnitude of current and voltage in case of DC. But in case of AC, we can change the current and voltage whenever required. Okay, so these are two things. There may be some other advantages, but these are main advantages. Instruments or device wise, there could be uh, some advantages. Okay, so anyway, so we have learned that we require AC, alternating current, and our modern age is actually going towards that. Like every electrical devices, like all electrical devices in home appliances or laboratory or industry, everywhere AC, alternating current, is being used. Okay, now we'll just learn about DC and AC current. How do we define, how to like how to recognize which signal or which current is DC, or what exactly we mean by DC or AC. So a current which flows in the same direction, current which flows in the same direction. So sometime we may say direct current is one whose magnitude does not change, or direct voltage is one whose magnitude doesn't change. Actually, that may not be exactly, or that may not be perfect definition of direct current or direct voltage. So the magnitude may change, it may change its magnitude but never change the direction with time. Actually, that is the actual definition. Okay, in lower standard books you might have learned that DC means it doesn't change its magnitude, the value is always constant. That is one part of the definition. Okay, its magnitude may be the same, it does not change its magnitude, that is fine, that is one kind of DC. But DC may change, DC signal or DC current or DC voltage may change its magnitude but never change its direction with time. Okay, that is actually DC current. Look, I'll just give you some example of DC current. Like see the example one, see it has a constant value. Okay, the current has a constant value. If suppose this is 5 ampere, then it is throughout, see everywhere as we progress or as the time passes, the magnitude of the current doesn't change. Okay, so this is one example. Another example, as I said, magnitude may vary but direction does not change. See here the current flow of the current is in one direction itself, because this is a positive value, it is always positive in the y axis, so it is always positive, it doesn't change its direction, but as well as it doesn't change its magnitude. But the second example, you see the current is flowing in the same direction always, in one direction. See always the value is positive, value is positive, value is positive here also, but magnitude is changing with time. Like see the magnitude is increasing, then decreasing up to 0, then again it is increasing from 0 going up to maximum value, again coming up to 0. So this is how it changes. So it may change its it may change its magnitude or vary its magnitude with time, but direction doesn't change. See here also, see sometime it is becoming 0 also. This is actually output of a half wave rectifier. We'll learn in semiconductor chapter. It is, see its magnitude is varying. At this place it is 0 actually, current is 0. But it doesn't become negative. Okay, always it is, so this is 0 anyway, this is again positive. Here see it is actually varying, like in the fourth example, this is also, see it is actually varying, its magnitude is varying like a wave. Okay, it is varying like a wave, but still it is not going in the other direction. That means always it is positive, this is also positive, this is Okay, it is becoming 0 and then again becoming positive. This part is also positive, this part is also positive. So the current is always varying in the, or sorry, not varying, yes, so it doesn't vary the direction. Okay, it doesn't vary the direction, doesn't change the direction with time, but its magnitude may vary. Okay, so this is about DC current. Now what is alternating current? See, alternating current is that current which changes its magnitude as well as its direction. Okay, a current whose magnitude changes continuously and the direction reverses periodically. See, this word is very important, periodically. See, I can have current which change its direction randomly. Okay, it can happen. See, it is also changing its direction, magnitude as well. But by saying alternating current, we are actually meaning that current whose magnitude changes continuously and direction reverses periodically. Its change will be periodic. Okay, I'll repeat this point, that alternating current means that current whose magnitude changes continuously and its direction reverses periodically with time. Direction reverses periodically with time. If I take this example, see, this is one sinusoidal, sorry, one alternating current. You look here, its magnitude is changing with time. Okay, by t half it becomes 0, and by t it become again 0, and it is going to the other direction. So this part is positive current and this part is negative current. It has maximum value here, it has maximum value here. Okay, and maximum values are same both side. So it is symmetric about the time axis as well as it is varying periodically. It is varying periodically. So since it is varying as a sine function, so it is called sinusoidal. So when we have an alternating current varying as sine or cosine, then we say sinusoidal. Sinusoidal, sinusoidal signal, we can say signal, or sinusoidal voltage or current. Actually, sinusoidal voltage or current is meant, like, whenever we say AC AC current or alternating current or voltage, we will take sinusoidal signal. Okay, it will be either sine curve or a cosine curve. It will be either sine curve or a cosine curve. So in case of cosine curve, it will start from maximum, then it will go like this, it will go like this. Okay, if I say here it is 0, so it is maximum here, then when it is maximum it will be 0, so here it will be again maximum, then it goes 0 here. Sorry, just a minute. If I draw cosine here, how does that look? So it will be 0 here. Okay, 0, it will go to the opposite direction, so it is maximum to 0 like this, then it is going this way. This is 0 means here it will be maximum, then it will be 0 here, then it is going to the other direction. It is 0 here means it will be maximum here, then it will come to 0 like this, again it will be maximum here, 0 here. Okay, like that cosine curve will go, cosine curve. Okay, cosine function with time. Okay, so we have learned that it should have a periodic change both by magnitude and direction. Okay, so that actually best uh, alternating current is the sinusoidal curve. Okay, sinusoidal functions. Alternating current or voltage can be represented best by sinusoidal voltage or current, right? So see, if I say sinusoidal voltage sine curve, let us say sine function v0 sine omega t. Okay, this is actually sinusoidal AC voltage. Okay, this is sine curve. So what is this v0, v, omega, etc.? Okay, sometime we can write this as v0 sine omega t minus kx also we can write. You might have learned this, or omega t minus phi. Let us say phi. You have learned in 11th standard this particular factor is called phase factor, and this phi is actually phase difference. Suppose this is v1, this is v2, so v1 and v2 has phase difference phi. That means this v1 is ahead of phi. Okay, like ahead of v2 by angle, phase angle phi. Or all right, so we'll just go with, now for the time being I'll go with zero phase initially, and see, if I send this alternating current in a resistor which has resistance R, then I can find out current as V by R, right? So V 0 by R sine omega t. Okay, this will be the current. All right. So both, like in a resistor, both voltage and current will be in the same phase. That we'll learn again. All right. So in this expression, you might have already learned what are the terms meaning. See, if I just take the voltage itself, so this V, it is called actually instantaneous value of AC voltage. I'll explain what it is. See, instantaneous means it is varying with time. Each each second or each time its value is changing, because this is a function of time. See, if I say 5 second, 10 second, 1 second, 2 second, every second its value is changing. See, these are two different instantaneous values of the same current. But the time you look here, time is here, time is this time. Instantaneous value of the current at this time, and this time is this one. Okay, this, suppose this is T1 and this is T2. So there are two values here shown in instantaneous value at different times. Okay, so instantaneous value means the value of the current which is always changing with time. That is instantaneous. At any instant, what is the value of the current? So if you just put that particular instant, you will get the value. That is instantaneous current or voltage. So that value is always changing with time. What is this V0? V0 is actually called the maximum amplitude of the voltage, or it is called peak value here. In AC, you will use the term peak value or maximum value, right? Maximum value of AC voltage. Peak value or maximum value. See, this value is actually constant. You look here, this is the peak value. Here actually I have shown in the figure as current. So I0, this V0 by R can be written as I0 sine omega t. You can just look from the figure. I is equal to I0 Okay, I0 sine omega t. So I0 and V0, these are actually, this is for voltage, this is for current. I0 is the peak value of the current. And here in the graph, I have shown you for the current, not for the voltage. I'm sorry. I think I have erased everything. Okay. So we have learned, okay, let me just tell you about current itself. I is equal to I0 sine omega t, so that you are not confused. So this is instantaneous value of current, and this is peak value of current, peak value of current, AC current, okay, alternating current. Okay, instead of writing AC current, better to write alternating current actually, or AC, just simply AC or alternating current. But when we use voltage, when we say about voltage, then AC voltage is fine. Okay, so what about this omega? Omega is angular frequency, as you know. Omega is 2 pi f. Okay, f is linear frequency or just frequency, frequency. Okay, this is called angular frequency. So these two are actually having different units. Okay, so when we write omega, its unit is actually rad per second, radian per second. Okay, radian per second. But when we say this, we'll write per second, because this is per second, or hertz, hertz AZ. Okay, per second or hertz. All right. So we have learned what is I. I is the instantaneous value, which is a function of time, which changes at each instant. Okay, that means this gives the value of current at each instant, and I0 is the peak value or the maximum amplitude of the current. Okay, and in case of AC, I have both maximum in the positive direction and in the negative direction also. Maximum of the current in the negative direction and positive direction. Okay, both directions I have. Okay, here, so here it is minus I0, here it is plus I0 in the positive side. Okay, all right. So I think, yeah, we'll just go ahead. See now, how is AC current or voltage generated? Actually, AC EMF, let us say AC EMF generated. This we have already learned in induction chapter. I I would like I would like to just recapitulate for you. See, AC EMF or alternating EMF is generated by rotating a loop, conducting loop in a uniform magnetic field. So, by rotating, answer is by rotating a conducting loop, a conducting loop in a uniform magnetic field. In a uniform magnetic field. So that is actually alternating, that is generating alternating EMF. How do you know? See, if I have uniform magnetic field and you have a loop like this, so as you see in the figure, uh, so what will happen? There will be flux linked with this, okay? Flux linked with that means flux means what? The number of field lines passing through this area of this loop perpendicular to the plane of the area, okay? Then we get that flask, and this flask is, say, if this, okay, the flask is actually written as, magnetic flux is written as B A cos of theta magnitude, okay? Now if the loop is rotated with angular frequency omega, so this is rotated with angular frequency omega, then we can say at any instant of time this angular displacement theta will be omega t, right? Then I can write BA cos omega t. Now according to Faraday's law, we know Faraday's law of induction. What we write? EMF E is equal to, okay, so minus d phi by dt. So here we will get BA omega sine omega t. Okay, so this is, see, this particular term will, if we write V0 or E0 EMF, and this is E, so we get sine omega t, right? So this is how we generate alternating EMF or AC EMF, okay? And this is called actually electrical generator or AC generator. This way, this construction is called, or this way of generation of EMF is called AC generator. Okay, this is called AC generator. Okay, so AC generator, when somebody asks you how do you produce alternating voltage or current, you have to say using AC generator. Okay, that's all. Now see one thing here, we have, okay, let me just go to this point itself. We have sinusoidal voltage like this, okay? I'm just taking one cycle itself, okay? Okay, it may not be perfect sometime. Okay, let me try once again. Okay, so we have, suppose this is current, so peak value here I0, this is positive I0, and here it is negative I0, so this is negative. So this is for a full cycle. See, this is half cycle T by 2, and here it is T, and this is actually sinusoidal curve, sine curve, okay? This has value I is equal to I0 sine omega t, okay? So if we take, see, if I just see, okay, one more thing I just forgot to tell you. So in case of circuit diagram, AC signal is actually denoted by this, okay? AC signal is denoted by this, a wave inside a circle. So suppose I just draw AC source which can produce AC EMF or give AC EMF to a circuit, and I have some circuit, okay, some bulb and some other appliances and all are there. If I want to measure the current in this circuit, when I know the alternating voltage plus minus 12, suppose AC, so here what will be the current? If we use this normal ammeter, normal DC ammeter, okay, normal AC ammeter, what is the value we see in ammeter? What is the value we will see in ammeter? You know what this normal or DC or DC or normal ammeter does? It actually sees the full cycle. It sees the full cycle and then gives the result, mean of the result, mean of the current, mean of the current. So what this ammeter does, it take both the values and then take the mean, just simple arithmetic mean. So I have I0 here and I have minus I0 here. So what is the value this ordinary ammeter will show for the current? So it will show zero current. I in the circuit is zero. But it is not true, right? It is not true. See, current is not zero in the circuit. Why we are getting zero? Because the ammeter, normal or DC or ordinary ammeter, is just measuring the mean value or average value of this AC current in a complete cycle or full cycle, in a full cycle. So that's why we are getting just zero. If I take average, average means what? Simple average, arithmetic average is this by 2, 0. So now we'll see. Okay, let me tell you how it is happening. See, if I want to take time average of AC signal, AC current. So if an alternating current is passed through an ordinary ammeter or voltmeter, it will record the mean value for the complete cycle, and that will give you zero. But see, there are ways to define average value of alternating current. There is a way to define average alternating current, average value of alternating current or voltage. What is the way? Let me tell you. Suppose instantaneous current I is equal to I0 sine omega t. I0 sine omega t. So I have to take average of it. So there is a way, or mathematically simply we can write, see, I average for a full cycle, say, I'll say, or see, it is denoted by this also. I'm writing another way. I bar is also I average. This I'm writing as full cycle, FC, full cycle, full cycle. How to define that? In full cycle means, suppose full cycle, the time is one, see, time is, total time period is capital T. So 1 over T, 0 to T I of T into dt. So this is actually average value. This is the way we write average value for a complete cycle. So if we write this and take the integration of this I0 sine omega t, let us see what we get. 0 to T I0 sine omega t into dt. So I0 divided by T, 0 to T sine omega t dt. So what is the sine omega t? If we integrate it, it will be cosine with a minus sign, and this omega will come numerator. with the minus sign. I'll write the minus sign here. And cos of omega t in the limit 0 to t. See, cosine of t, see omega t is equal to again, or t is equal to 2 pi by omega. This we can write. Okay, that will write here. So I'll take the lower limit first and making positive here. Lower limit is 1. Cos of 0 is 1 minus, see, cos of 2 pi. It is coming cos of 2 pi. Cos of 2 pi means also 1. So this 1 and 1 both will give you 0. Cos 2 pi is 1, right? Cos 0 is 1, cos 2 pi is also 0. Sorry, cos pi 2 pi and cos 0 are actually the identical value. So you are getting in a full cycle. So that is why reading will be reading in voltmeter and in ammeter. Reading in voltmeter and ammeter will be 0 in full cycle. This is in full cycle. That means, it is not the good way to define an average value for alternating signals. Okay, so that's why there are two ways to define average value. So average value in half cycle. So this is one way of defining average value of the average value of the alternating current. So that is denoted by IAV, say, and this is written as, see, IAV 1 over t by 2 and 0 to t by 2 sine I0 was there, I0 sine omega t dt. Now if you do this, look what we get. 2 by t, 0 to t sine omega t, this I0 will come here, sine omega t dt. Actually the integration is same, but limits are different now. Okay, so what will be there? Here omega will be here, and it will be cos of omega t with the minus sign. I'll just make the limit like this. Okay, so upper limit, look here, cos of 0 means 1, so 2I0 by omega t is 2 pi, right, as you have seen. So omega, okay, 2 pi by, so omega t, see, t means 2 pi by omega, so omega goes up, so it will be omega into t means 2 pi. If you are not able to understand, let me write it. Omega is equal to 2 pi by t. This is the one. Okay. So omega t will be 2 pi. Right. This is easy to understand. So omega into t is 2 pi. So 2I0 and this is 2 pi. And here look, cos of 0 is 1. And say omega, if I write cos of, say, omega t, this is t by 2 actually. Sorry, this is t by 2. Omega 0, this is t by 2. So t by 2 will be giving you pi, isn't it? Cos pi. So this is actually cos pi. So 2I0 by 2 pi into 1 minus of cos pi means 1 again. So you will get actually 2I0 by pi. Look this point. So average value in case of AC we generally take in half cycle. So and half cycle in half cycle the average value of current or voltage or any AC signal, I average is actually 2I0 by pi in case of current. So 2I0 by pi. 2I0 by pi. That means what? 2 by pi times of the peak value. 2 by pi times of peak value of current. Peak value of current. Alternating current. Or here, yeah, alternating current. Okay. So we have got a relation between average value of current in half cycle with the peak value of the current, AC current here, alternating current. Okay, so the relation is 2I0 by pi. See this 2I0 by pi, so I'll write here average or mean value of alternating current in half cycle or during half cycle is I average, okay, is given by is equal to 2 by pi times I0. Okay, that means 2 by pi times, that means I average is actually around 63% of around this much 63.7% of I0. That means this average value of alternating current in half cycle is just 63 percentage of the I0. It doesn't give you the full magnitude of the alternating current, neither it gives zero. It is actually 63.7% of I0. So this is one type of way or one way to describe the average value of the alternating signals or alternating current or voltage. Now I will see another effective way, very effective way of representing or expressing average value of alternating current, that is RMS value. RMS means root mean square value of AC signal. Signal by meaning signal means either it can be voltage or current. Okay, so what is this RMS value? Root mean square value of AC signal is RMS value of AC. How do we define AC, like RMS value of alternating current? Actually, this is actually sometime okay, it is defined as the value of direct current. Okay, RMS value of AC signal is defined as the direct current or equivalent direct current. The equivalent direct signal, I'd say. So better to write here alternating current itself. Alternating RMS value of alternating current is the defined as the equivalent value or equivalent value of direct current or equivalent direct current which produces the same heating effect same heating effect same heating effect in a given resistor as is produced by as is produced by an alternating current. Alternating current. Okay, one more point is when passed through same time for a same time when passed through for a or for the same time for the same time in the sense time interval, and it is denoted by IRMS in general. Okay, IRMS. So let us derive the relation then between, see, in case of average in half cycle, we have seen average means 2 by pi times of the peak value. So is there any relation between RMS value and the peak value? Let us find out that. Okay, so just a minute, we'll just go to the next point. Okay, so we are actually finding out IRMS. Let me just do one thing, get this particular figure here. Okay, so yeah, it will help me to explain some points here. All right, so let us consider that an alternating current. Let me just take a representative circuit. So this is alternating which is sent signal means current which is sent through a resistor R. Okay, so this is actually giving current or passing current through this like this. Okay, I0 sin omega t. So in dt time, what is the heat generated? Heat generated generated in dt time. Suppose that is dH, that will be then I square dt. Okay. Now if you want to get the total heat generated in full cycle, so how we write? We write 0 to t I square dt. Okay. So this we can find out. Okay, I square dt, that we can find out, doesn't matter, but let us find out the relation. So let me take the effective DC value, effective DC current, DC current as IEFF, effective, right? So it will also produce the same heating effect, right? Then H will be IEFF square into R into T in full cycle in case of DC. So this is effective DC or equivalent DC, equivalent or effective DC, which, okay, so effective or equivalent DC current IEFF. So that also will produce in the same. So if I just send I effective current from DC, okay, DC source, I effective, I am sending current I effective through this for a time t, so it will produce the same heating effect. So from here I can say, from the definition we say that this effective value or equivalent current will produce the same heating effect. So I can write IEFF square R into T is equal to 0 to T integration dt, like this I can write. Oh sorry, there will be R also here, I square R here. Okay, so here also there will be R. So from both sides, R is a constant value of resistance of a resistor. Okay, so resistance value will be not changing with time. So this R goes off from both sides. See, I can write this I effective is equal to 1 over T 0 to T I square dt. Okay, this is square, right? So this I have to see, RMS means this effective current, right? RMS means this effective current, effective or equivalent DC current. So that is IEFF is equal to square root of 1 over T 0 to T I square dt. Okay, so this is the value. So then what we are getting? See, this inside this value, you know, this is what? This is actually the average of the square of the AC current, average of the square of the AC current, right? See, average, see what we have written in time average. Okay, average of the, so average we had written 1 over T full cycle 0 to T I dt. So when I write I square dt with integration limit 0 to T 1 over T, this means average of I square. Okay, average of I square in full cycle. Okay, FC. So look, then we can write IRMS as square root of the average of the square. Okay, square of the current. You might be a little bit confused, so I'll just write. This is a way to derive the relation between IRMS and the peak value. So we'll get it here. So okay, so let me do it here. I is equal to I0 sine omega t. I'll just finish with this. So I square means I0 square sine square omega t. Then if we take the full scale average of this square term, it actually will not give you 0. It will not give you 0. All right, it will not give you 0 because now it is I square. Even if we take minus I0 whole square, that will give you positive value only. Okay, so this is how this will not give you 0 in full cycle also if you take the square of the alternating current and then take the average. Okay, so we get here I0 square by t. So this part we have to do the integration. So 0 to t. Let me just multiply 2 in the numerator, 2 sine square omega t dt. Okay, so I have to multiply 1 2 in the denominator and 1 2 in the numerator. So 2 sine square omega t can be written as, so now this part alone I'll write, then okay, let me write this also. So or I0 square by 2 I t0, sorry, not t0, t 2 I t is the time period. Okay, 0 to t, and this will be 1 minus cos of omega t, 2 omega t, actually cos of 2 omega t, because you know, like 1 plus 1 minus cos 2 theta is 2 sine square theta. Okay, 1 minus trigonometric identity, we know 1 minus cos of 2 theta is equal to 2 sine square theta. Okay, 2 sine square theta. So that is what we are doing here. Cos of omega 2 omega t we have to integrate over a full cycle. See, over a full cycle, cos omega t, 2 cos omega t, 5 cos omega t, 6 cos omega t, or sin omega t, 2 sin 2 omega 2 omega t, 4 omega t, whatever omega t you take, it will give you 0 in full cycle, isn't it? Because anyway, so two frequency may be different, but the nature of the curve is like this itself. So you have positive and negative both. You're taking average of that in full cycle will give you 0. So this term will be always 0. So only we will get contribution for that. Okay, let me just write that contribution here. So what is there here? Then we get I0 square 2t. Here 1 2 omega will come. No, yeah. So this will be totally 0 anyway. So it will be again t here. Okay. So this t will be gone. So this is actually this value, this average if you take. So average you are getting average, square average you take I0 square by 2 you are getting. See now here if we just put this value, so I'll get IRMS. So IRMS is square root of 1 over t 0 to t I0 square. Oh sorry, this is simply I'll write I square dt, which is nothing but I0 square by 2. Okay, I0 square by 2, and if we take the square root of that, I0 by root 2. So this is the relation between RMS value and peak value. See, this is actually, nearly 70.1 or 70.07. Okay, so nearly 70 percentage. Okay, you can say that nearly 70 percentage of the peak value. So RMS value of current is nearly 70 percentage of the peak value. Okay, I'll just show you here in the next. Yes, I'll just clean it. See here. So this is the peak value I0, that is maximum value. See, nearly 70 percentage of I0, which is actually RMS, IRMS, and average is less than that, nearly 63 percentage. Okay, 63 percentage of I0, which is I average. This is in actually half cycle. Okay, all right. So see, 220 volt AC is actually AC 220 volt AC equivalent to how much DC? That is, see, I have to find out I0. So this is actually IRMS. What is given? What is this 220 volt? This is RMS. So you have to find out I0. So I0 is root 2 into IRMS. So the peak value, or okay, peak value of that AC voltage is nearly 311 volt. Okay, this much volt. All right, so we'll discuss again in detail later about this. In the next class, we'll just take up new numerical problems, and we'll further discuss about phasor and phasor diagram. Okay, so thank you for your presence. Bye for today.